Okay, so we'll go ahead and get started here. So we have a couple of reactions up here, and I just thought, well, they're all in solutions, so they're forming an aqueous solution, aqueous, however you want to pronounce it. And then notice that these are double replacement reactions, and it has a question mark after that. So would you like to go over the top one or the bottom one, or? Okay. So then when we look at iron 3 chloride, what's the symbol for iron? Okay. And then the chloride ion. Okay. Then, like it says in the green, that's an aqueous solution. Okay. Then our sodium chloride, so we've got what? Okay, which is also an aqueous solution, as stated earlier. So, and we're told that it's a double replacement reaction. We know that chlorides are soluble, okay? And you might look at this and say, now, wait a minute here. When you're using these, if you're told it's an aqueous solution, it's going to dissolve. But when these two react, this is where you use this as a tool to see if a reaction is going to take place. Because there again goes back to what we see happening here. When something falls out of a solution, then we call that a precipitate, which I probably really should go and wash this pretty soon. And well, actually, let it dehydrate so I can get rid of the solid and dispose of that properly. All right. So let's look to see what do we form on this side, and do we form a precipitate? So we have, are any of these subscripts going over to that side? No. For sure. And maybe, but let's look to see what we have. I heard Fe, and what would iron bond to? Hydroxide. Okay. And then, and we can, do you want to finish the compounds or finish the reaction first? Reaction. Okay. So if iron's bonding to hydroxide, what is sodium bonding to? Sodium chloride. Okay. So as we look at our papers then, and we look at the rules, okay, and we find our ions on here, and must be optimistic today. Optimistic, it's going to be a good day because it's sloping upwards. There we go. So is that side written correctly if this reaction proceeds? No. It is not. Okay, and again, and this will possibly happen too. We've got one hydroxide ion, but we want how many? 3. Okay, so therefore we have to do this. Okay, and do we need to change anything over here? No. So that would be correct. Now, are chlorides soluble? They are extremely soluble. But is this chloride going to be soluble? I would think so, because you put any type of table salt in water or form an aqueous solution, it's going to dissolve. Okay. But then what happens when we locate the hydroxide ion on here? It says that, how can we be sure? It says There are some exceptions to that. But iron is not one of them. So just like when we poured those two solutions together last week, what can we presume is going to happen here? It precipitates out, so it forms a solid. That's right. Okay. So the next thing we would have to do is balance that. Okay. And we've got 3 hydroxides over on the right side and only 1 hydroxide here. But this might not work out the way that we would like. It's just trial and error. So let's try 3. Your hydroxides are balanced. Okay. And now we've got 3 to 1 with our sodiums. So we need a 3 here. Okay. So sodiums are balanced, hydroxides are balanced, and it's just a coincidence, our chlorides are now balanced. Okay. So that would be correct. All right. Front row, are we on the bus here? And back row. Okay. So then, I think it's fair to ask, well, say, you can make this practice as simple or as difficult as you would like. I wouldn't say difficult. What I mean by that is we would want you to pick one of these 2 to work with. I would say this one. Okay? So then, how many, when I say it's simple, do we have moles of sodium hydroxide to start with or grams of sodium hydroxide? And if it's grams or if it's moles, we need a number. Okay? So how many grams of this do we have? So if we have 60 grams of sodium hydroxide, how many grams of this are we going to produce? Now, this is why this is significant, because if we had, let's say, for instance, magnesium. No, not magnesium. Barium. I just wanted something out of column 2. Because if we had barium here instead, yeah, this is just, if we were to change this just a little bit, okay, what happens if and when barium bonds to hydroxide? At least it's insoluble because it's an exception. It's insoluble?
No, it's soluble.
Well, it's got to be one or the other. Can't. So then, if this is soluble now, all you're going to have is just a beaker like this. Okay, you would have just a simple beaker like this, and you're looking in here, and then there's nothing to really measure. All you have, you can't even see any layers in there. So you'd have your barium hydroxide and your sodium chloride. They're aqueous solutions, and you can't see anything or measure anything. That's why we use this as a demonstration to show that when something precipitates out, we can form that solid. So then that actually forms on the bottom that you see here. And that's something that you could measure because that will precipitate out. But go back to how we had this, iron, and then iron here. And then, of course, 3 here. All right, now we can get rid of this. So now, okay, we're not going to measure this. Although for your paper today, all reactions that we work with are ones that we're just going to presume that we want you to make that measurement, whether it precipitates out or not. This is just being a little more specific, so therefore we need to see, well, how many grams or moles? Okay, so then if we had 60 grams of this sodium hydroxide, how many grams of that iron 3 hydroxide would we make? Do you want to work on that on your own or together? Okay, so therefore I will hit pause here for just a moment and we can proceed from there. We'll go ahead and get started or continue this. Now, what's wrong with what you see here? Anything?
You don't have labels.
Yeah, I mean, it's just a good idea to show this as we cancel out our factors so you know where it is you're actually at in the problem. So then, if we're starting with 60, that's true in step 1. We've got 60 grams of sodium hydroxide, okay? And I believe, is it 40? Is that how many grams per mole? I just did 23 and 16, so 39, so 40.01 it looks like. Grams of sodium hydroxide. And that gives us one what up here? A mole of sodium hydroxide. So now we're in moles of this substance. And now we can get to this side of the equation or reaction. So how do we cancel this mole out in our next step? So for every mole of sodium hydroxide, we get moles of iron hydroxide, okay? And again, you can abbreviate this as long as you know what it's pertaining to, okay? Are we done in this step because it's a mole ratio?
No.
We are not. Okay, so we have one.
Would you have
Up here? All right. Or over here? So then these are gone. Now for every mole of iron hydroxide, I don't know, I thought it was 109. Okay, and I could be wrong. So 55.85, there's our iron. 16 times 3, 48. Okay, and then 3.03. So 8. Okay, there's our decimal. There is 8, 16, 1, 9, 10. I said 109, didn't I?
Yeah.
So it is 106. Okay. 0.88. These are now gone, so therefore we can multiply across and divide by about 120. What I mean by multiply across, 60 times 106, and then 40 times 3, it's 120.03, and then that gives you an answer of approximately what? 0.43 grams of iron hydroxide. Because what will happen with this is we could also do this as what we call something called a percent yield. That's what's nice about this activity, okay, that we'll probably do later on this week, okay? Because on pencil and paper, you can calculate out what we think we should get, and according to this reaction, we should get around 53.43 grams of iron hydroxide. Although the chances of that happening are quite slim, that's probably not going to happen. So there's no way we can get every little bit of that precipitate out and then measure, okay, this is going to be a reaction that gives us 90-some% accuracy. I mean, possibly, but not with the lab ware or materials that we have. Okay, So that's what's nice about these activities is it's showing you that you can actually grab some raw data with that rather than just saying always working in problems in the book. That's just setting us up for being ready to get actual data and see, okay, now I really understand what's going on in these compounds. Okay, back row, are we on the bus? And front row. And think about how much you've grown since the first few days that we've gone over the back of this. And are you going to make mistakes? Yes. I mean, I think it would be silly to say that we're not, because do or did we make mistakes on the football field?
Never.
Okay. The volleyball court. Okay. And in basketball, that happens too. I mean, we dribble into a trap, or we possibly turn the ball over. I mean, it happens. But that's why we try to learn from those mistakes. Okay. So then, as we look at this next reaction, okay, what is the symbol for Ca? Ni?
You just said, what's the symbol for Ca? No,
Oh, what's the symbol for calcium?
Ca.
Ca. Okay, I did this. See if we're paying attention. What's the formula for the nitrate ion? Okay. And we remember we had aqueous up here. Okay, plus, what's the symbol for potassium? Okay. And again, I put these too close together all the time. Aqueous solution. Okay. So we had double replacement, like up here, question mark. Okay. Is everything written correctly on our reactant side? Okay, so this is +2, this is -1. So the least common multiple is 2. 2 divided by 1 gives us 2. So we need 2 ions, so this has to go in parentheses. That gives us that. Then what do we see about the potassium hydroxide? +1 and... So then what's going to happen is the charges will not change, okay? So then what we see happening is, what would we get on this side? I mean, the reaction is going to proceed. That is true. But there's a little tricky component to that, possibly, just like there was for this. Okay. Calcium and okay, and then potassium and so did we have to bring that 3 over? Did we have to bring this 2 over? No, because the 3 is part of the formula. That's why that's here. But notice we still don't have this written correctly yet.
I guess you could put your OH in
Okay. All right. Okay. So these do I suppose you could say they mix with one another, but what is the major difference between these two reactions? Well, I suppose you could say that they do mix with one another. You just can't measure anything. So, but that's why this would be a little tricky. But again, the paper that you get today everything will react to give you data. It gets to be a little more specific when we start talking about this with the aqueous, the solid, and other natures. Okay, so is there any oxidation or reduction taking place? We haven't asked that in a while. Is there any oxidations or reductions taking place? I mean, we've been talking about that all the way up to this time. Are you saying that there's no oxidation or reduction? Well, let's look. Yes, nothing has changed. So you don't have to have an oxidation/reduction reaction to take place just to say we're going to be able to measure something. This is evidence of that. So your oxidation and reductions is mainly for single replacement reactions, not double replacements. Because like we had mentioned, nothing here has changed. The only way that we could say that is if we were to do this, if we had some calcium nitrate and some potassium, and if we add that to it, now we could say this single replacement reaction might take place. And then, of course, that's not aqueous solution anymore. This would be what? If it's a metal. Yeah, it's a solid, because this isn't chlorine, it's not oxygen, it's not nitrogen, it's a metal, so therefore it's a solid. And then if that's a metal and it's a solid, what's this going to be then? It's going to be a solid then as well. Okay? And then we could say, well, calcium was +2. What's it over on this side? It's charge of 0, so it went through the process of what? That was reduced. Now we see potassium went from 0 to +1, so that went through oxidation. Okay. Then, if you really want to be specific, we say calcium is the oxidizing agent, potassium is the reduction reagent. Okay. But I just want to put this back up here for practicing purposes. This was this OH we had here? Yeah. Okay. So then this was OH then as well. Now, again, just as for some of us tuning in a little later, we look at this and we see, once we find hydroxide, we say, well, that must be a solid because it's listed under the insoluble portions. But then when we look at exceptions to that, we see that calcium is an exception, so therefore this would be an aqueous solution, and it would dissolve. Okay. So you could, for like on our purposes, say if we had 15 grams of this, how many grams of this are going to be made, even though you really can't measure that because you don't have a precipitate that falls out. Okay. So it says assign worksheet 1 and on plan book I think it says worksheet 2 as well, because these problems do take quite a bit of time. So is there anything such as homework anymore, where we're actually here at school, now we're at home, and I'm at home, I open up my backpack or whatever it is that you have, and you pull out your algebra, your chemistry, your English, whatever it is. There's no such thing as homework anymore. So, and this is just a valid question. If that's the case, we probably don't have to have this. Maybe this should be the 10th instead of the 12th. Because you say you don't have any homework. That you take something home and actually work on it.
We don't need homework though. That's what school is for.
Yeah, I learned everything I need to know right here.
Okay. So as you're tuning into this, and I'm going to have to mention this to your classmate because she doesn't have the front side here. Does have this side and then has the other paper here. And keep in mind that you're not always given the chemical reaction. Now, all these react, all of these will give you data. We're not talking about something like this. That will be for later. Okay. So the rest of the time then is yours.